Okay, I'm gonna be watching Mark Harrison, UCLA, Himalayas, or Himalaya. And it's called 10 Untenable Ways to Make the Himalaya. So I thought this was a really good topic to check out because it's gonna be, here are the models and here's the problems, which is usually usually a very revealing process to go through. So I look forward to seeing. I'll just play. I'm probably going to do two halves, record this because it's an hour or 40 minutes. I'm probably going to record this in two halves and hopefully be done in 4 hours.
And I haven't been really seriously contradicted, is that something like this extent of thickened crust and elevated terrain hasn't been seen on the planet since.
I'll just speed it up until technical stuff.
Since the Granite. So roughly in the last quarter of Earth history, we're fortunate to have arisen as a species at a time to be able to behold something this spectacular. As I say, the Himalayan mountains, the Tibetan plateau, its geology has inspired virtually every model about the building of mountain ranges, plateaus.
I want to know what this image is. I want to know. Have you ever seen the rain? It looks almost like it points back to, I don't know the mountain's name. I wish it would start zoomed out. It's near Korea. Let's get rid of this. There it is. Heaven Lake at the top of... I'm not sure. I think that's it. That's gotta be it. Right there. Does that happen to coincide with this in some way? I don't know what this is. Maybe if we look at the terrain, like this here kind of comes up there and does maybe come to right around there on this map. And has something here above it. Maybe that's what's above it, or even that. I just don't know what that map is. He doesn't actually define what this is. This must be a topographical map. Let's see if there is a bit of a flow from a cone that originates at around this. Is it possible that it's a particle over here? When the Earth supernovaed, it basically caused what's called the north-south gravitational alignment. North-south gravity alignment. The energy propagated into the continent and then deflected back because of resistance it felt, and just brought back island arcs, creating all the arcs, all these arcs, arc after arc, arcs within arcs. Here's an arc that's merge with this arc. Here's a second arc here. Arc. These arcs are not random. They're results from deflection of energy off of basically a craton type of structure that was sufficiently resistant to just stop the flow, because the Earth basically supernovaed and exploded in the Pacific, sending energy into causing the Ring of Fire, but especially energy into Asia. And so maybe as the Earth supernovaed, the nucleus of the Earth, which caused maybe, I don't know why it does, this was really early, this region of oceanic crust. So maybe, I'm kind of envisioning that that's where it's supernovaed, but it's clearly significantly prior, although it is rather explosive looking. So maybe there was an initial explosion in this time frame that really was started to just put pressure into the continents, and as it did so, time passed because the Earth was radioactively decaying and painting a picture of a significant amount of time, but really it was just building up the pressure until the bonds could break at 66 million years, which maybe coincided with the energy from this being able to reach the north-south gravitational alignment and maybe influencing a particle around here to both supernova this way, although I don't think the arc, especially considering this portion, is especially suggestive of that. It's more suggestive of over in this direction, I'd say, in line with this maybe. Looks like there's some lines there, sort of, potentially. Maybe more in that direction, it would seem. Here, I would think the particle was here that did this. Is there a degraded version, post-radioactive decay in a new stable state? Or maybe it's just gone, like a shallogram. Some of the particles are just gone. There's no particle there anymore. This has a particle. But it's a small one, so it's lost a significant amount of it, probably, compared to the larger particles. And they're getting flattened by pressures without a pressure from the sides, causing them to flatten and then to extend until they supernova. But frequently the particle literally is gone and has been used. The material of the particle is used to make the features that are not there without the missing particle, and then this feature that's like a frozen supernova of the particle. This one's just... another particle. So it could be like this, though, where part of the particle is missing. One of these I wanted to look at because it shows a collapsing side, suggestive that it had a pressure. Or is it? Here it is. So notice this. Here we go. Over here, there's this cave-in. And then it's so to me what was happening is inside here before the cave-in was a more normal shallogram structure like the others. Say that maybe. Just more like that, without this exiting of the rock, still within the rock though. No, not necessarily opened yet, although it does look like it maybe reached it, although it could do a lot of this like spontaneously, so that it really was more so a system here, but it was able to shape more the whole of it by some subtle existence of the system. It's fields. So what I've found really, what I wanted to look at this for is because I felt this one, probably because it has this collapsing side. The way I picture this is a particle, like an atom, literally, that has two layers above and below it that can compress the particle. And so it's just like it forms in different ways. So there's a rock like this is more just like like that, let's say, just a smooth surfaced rock, and an energy propagates through it, and it basically causes the particles within the rock to begin to separate, and they differentiate themselves based on the energy flow that's propagating through the rock, and it brings basically more dense particles to this center region where these chakras are just energetically occurring, because within the rock naturally there are layers that form that aren't even carved out yet, but are just naturally formed. And so when an energy propagates through it, it goes through a channel between the layers, where then the denser particles move towards, and then the less dense particles move away, causing an actual separation process. But then this rock's this is all occurring in a transitional period where this rock itself is still somewhat molten, so it's not so solidified that if it experiences some outside forces, that it would be able to hold its form, basically. And so it experiences an outside force, which is also interesting, just thinking about from like a philosophical standpoint of like becoming a solid form, so that outside forces literally are unable to reshape our being as an individual, is maybe a thing that's possible, and vice versa. So, to me though, I was thinking there's a good chance what happened here is something like either this rock is lying on this side, but that didn't really make sense to me. I thought maybe more likely something was physically on top of it, although this curvature may, like, it may be, I think this is the same one. Oh, here it is. Here's that indentation. So, like, it could be that a rock, like one of these, was physically pressing down on it with its weight. But as we can see inside, that where it's pressing was not over top of the pillar system, the particle that forms a pillar between the layers, where energy is focused through the layers. And so because of that, it was pushing on this weak point over here, where there was a literal empty space for larger particles like atoms to flow into if pushed by an outside force into there. But essentially it was stable because it's filled with ether particles and heat, to a point where it literally created a void that was stable, but like unstable. Any outside force on the still malleable rock would cause a influence on the rock like this. And then interestingly, so that's the thing, it's like a surfboard. Like if you're standing on the back of the surfboard, then it's kind of like, or one of those one wheels. It's like a one wheel. Here's the one wheel. And then the board itself has the weight more so on the back, and here it just wasn't stable enough and it caved in. And so literally, like, the golden supernova remnants aren't over here where it caved in. They're actually in the opposing direction because the surfboard type squishing basically directed the flow of propagating energy from whatever this system was doing, so that it would essentially cause the mountain chain of the Himalayas to be expelled beyond the edge of the crust and also lift up the Tibetan plateau. With this space in the system. But like, there's a system like this under the Himalayas, literally producing the side of the shallogram of the Himalayas. So like, it's probably not over there, it probably is over here somewhere. And this really suggests it's over here, but this, back to the video. Now that I've made it a minute in, 16 minutes, I said, what did I say? 2 hours, 4 hours, hour 40 equals 4 hours? Yeah.
The decay of these mountain ranges. Its ultimate formation, there's general agreement that it's because until about 55, 60 million years ago, India was an island in the Indian Ocean, and it then plowed into the southern margin of Asia and has moved forward and somehow built the Himalayan Tibetan orogenic system. Despite the fact that, I have colleagues that are, I'm looking at the, Proterozoic of Norway, trying to understand the Caledonides of Great Britain and understand ancient origins. And I just can sort of sadly shake my head, because here it is. We've got the seafloor magnetic anomalies. We know the path of India right over the last 60 million years and before. We have the geodesy in hand. We've got
right at the edge of the opening here, I noticed there's 2 little dots past the edge of the opening. I think I can see them on the camera. But they're physically openings, which I found really interesting. Just these little dots. It's like the process was beginning by carving a little opening, but it didn't actually, like, it finished. And so the little opening was just a little opening.
Got seismic imaging of the crust and mantle lithosphere. Tomography below that. We can wander all over the plateau and do geological observations and make measurements and date rocks. And there is no agreement beyond really these 2 statements. And actually, I think about it, there's a group that actually is advocating that the collision didn't begin until about 30, 35 million years ago.
So just the first statement. The first statement is
No, that's pretty much just me, actually. Now that I think of it. But people say, what about the Pan-African? And actually, if you look in detail, at no point in time was there ever you look for granulite terrains as a proxy for crust that would have been 70, 80 kilometers thick. And no, not at any one time, nothing like this occurred then. So it's a bit ironic that, this is the so-called greatest natural laboratory for understanding orogeny. And, we've, as I said, British geologists were climbing over these rocks in the 1870s, 1880s, and actually making some very important observations that, we're still debating today. Initially, here's this famous prescient paper of Argonne, 1924. This would be north and south. Here's India, and you can see that he has India under thrusting the Himalaya. Here's the Kunlun range. Here's the Tarim, and the Tian Shan. And by gosh, pretty amazing pre-plate tectonic perception. But that's pretty much until the 1970s, 1980s. These models were largely just sort of schematic cartoons. Then a series of developments, numerical developments, creating more and more sophisticated models. Today, in fact, we have fully coupled thermochemical models that engage both the the mantle and crust, and we can evaluate the effects of climate,
Pardon me.
and localizing deformation, things like that you've already heard about. And of course, the future has no bounds. But what I really want to drive home is that this is a part of the world that basically inspires models that we can squabble about. Okay? And this is not exhaustive. Okay, this is simply starting with argon all the way. In fact, we're going to talk in some detail about these two, but actually, I will address virtually every one of these. I don't mean to suggest that this is the extent of it, but these are the ones that, yeah.
In the 20s, I just never really was aware of that. But so there, the plates are moving forwards and back, but no plate tectonics. So how did that actually? People were fine with that?
Well, of course, continental drift was popular in some quarters at the time, and it was, this has been the fundamental puzzle of geologists, right? Which is that, geez, that's a thrust fault. That means there was horizontal motion, and well, of course, you know that the history of geophysics has been essentially, the history of setting back Earth science, tens of years. Alan, come on, engage me here. Starting with Kelvin.
There's a lot of
Jeffries was at the time very influential, and so argon is he's a physician living in Paris.
Sorry. Come on, engage me. I think he said. I'm looking captivated at the little things. I'm trying to literally zoom in on it with my focus. Literally not, therefore not engaging him. Pardon me, sir. Pardon me, Mark. I'm what if I can heal my eyesight by caring enough about seeing these that I just focus on them? Because I think that's an issue, is I'm just kind of aloof consciously, and it literally causes me to not focus with my eyesight, and to a point where it begins to go out of resolution. It's not a inherent nature thing. It's more just a habit that is me and a lot of people. That's the nerd concept. Why? Because people are not paying attention. They're off in space, and it causes literally, that's my thoughts, a tendency, maybe not individual completely, where it can also be generational by ripples through layers kind of thing, but
And he eventually gives his practice up because he's so engaged, and you can imagine that it would be sort of the Sven Hedin accounts coming out of the early trips through the backwoods of Tibet. And actually, that I mention it, if you just hold that thought, that actually the Hedin expeditions have really inspired what's been the current debate, the last 30 years or so of distributed shortening, or the thin viscous sheet model it's called, versus continental extrusion. We're going to talk about that. That was actually inspired by the fact that in at 1911, Sven Hedin and his group are wandering through the mountains of Tibet, and they notice, in fact, Cretaceous Granites. And they pick them up, but they're being chased by Compa bandits, and they forget to wind their chronometer, so they don't actually know. They know their latitude, but not their longitude. So this actually was inspirational in the sense that it then became sort of well agreed amongst Western geologists that, Tibet must have been basically planed off below sea level, 90 million years ago, because everywhere there's the marine fauna, and as it turns out, it's actually restricted to a fairly narrow channel. But this is, in fact, this is the one origin, because of the fact that post-war, Western geologists could wander all around the world except into the backwaters of Tibet and a few other places. So this is a case where actually numerical models got to the origin before basic geological observation. And in some respects, we've been suffering for it for the last 30 years, that basically the modelers beat us to the outcrop and put into place concepts that sort of were so widely disseminated that it's really been hard to with subsequent observation, beat them out of the literature. Okay, so what we're going to do actually in turn is really talk about each one. And I'm not, I'm a partisan. Okay, I've made my observations, and I'm going to contribute to the problem as much as the next guy. But what I thought I would do is give you as objective as I can an evaluation of these different models. This one here for the last 10 years has swept the community like a wildfire. This is as close to religious observation as I've seen in the geosciences, the channel flow model. And we'll talk a bit about that, which I don't think is tenable for reasons I'll describe and get you guys to point out my flaw. With Nelson, it is actually directly inspired from the Nelson model, absolutely. Yeah. But much modified since. There are some untenable aspects that. Okay, so I'm going to focus mostly on the crustal thickening history, although ultimately, what's Tibet doing up?
Okay. I just remembered I had this faster. It would help to not do that now.
There, this average elevation of 5 kilometers. Surely it has to have, some involvement of the mantle as well. But Wang Ping's going to talk next week. He's going to focus on, seismic imaging and the deep earth aspects of this. So I'm really going to restrict for the most part, you'll see a couple of cross sections, to crustal thickening history, and kind of artificially divorce that very important and arguably dominant element from this. Okay, so these are what was the crustal structure of Tibet prior to collision, be it 35 or 60 million years ago. As I say, there was a school of thought that in fact it was everywhere thin. This inspired the so-called thin viscous sheet model, came out of Cambridge in the late 70s, early 80s. Phil England, Dan McKenzie, Greg Hausman, later Peter Molnar, all advocates of this point of view, which is simply that they, at the time, the numerical sort of state of the art, I guess Peter Berg was the originator of the thin viscous sheet, basically a 2.5 dimensional model where you take an average crustal strength, lithospheric strength in the vertical dimension, and then, in this case, apply an indenter, okay, numerically here, and what they saw was, as India here hits the margin of southern Asia, you basically like plow up as a bulldozer the crust in front of you. So here's 1, 2, 3, 4 kilometers in elevation, and then they pointed out that this looks a good deal like the present topographic distribution of Tibet, southern Asia. In detail, was high elevation established first in the south and then uniformly propagated north? I think that's no longer viewed as consistent with the evidence. But this set off a 30-year debate because also in the early 80s, 1982, in fact, a variant of this appeared on the cover of Geology. The so-called escape hypothesis. This is Tapinier and his co-workers doing a very simple experiment. This is plasticine. You see the stripes as a strain marker, and they push a rigid indenter into it. And because of the nature of this material and the fact that there's a glass sheet over here to constrain it, in fact, it responds by breaking chunks and pushing stuff to the free boundary over here. And this was Paul's analog for for in fact the extrusion of Indochina, of Sundaland, which I'm going to show you in the next slide. But just to point out that this really has, over the last 30 years, broadly dominated in the background of every discussion you have about possible models to explain the origin. You have partisans that say, this is the important thing. You need every last centimeter of the 2,500 or the 3,000 kilometers of convergence, depending on when you want to start collision, right? Where is India relative to the boundary of southern Asia when collision begins? So if you think that rudite that Hedin and his colleagues picked up is telling us that Tibet was planed off below sea level 60 million years ago, you need every micron of that 2,500 kilometers of convergence in order to build a crust that is today 75 or 80 kilometers thick. If Tibet had locally some high topography or some elevation or in this crustal thickness, then in fact you actually can use some of that convergence to push chunks of it out of the way. Okay, geologically, one of the observations that the English geologists made 140 years ago is this paired granite belt that, it's in many convergent margins. You look at the Andes, and there's, calcalcaline, plutons and volcanics, linear chain. The Himalaya is a little unusual in that there's two belts of perluminous, these so-called S-type granites we mentioned the other day, to referred to as perluminous, that are offset by about 80 kilometers, and they run parallel to the origin. And this is essentially unique in origins. More recently, again, this is sort of swept like wildfire, the idea that it really matters which direction the rain comes from. Okay, you have the Indian monsoon come up, hit the southern margin of this extraordinary mountain plateau system. The rain, where it washes sediment, changes, loads the frontal basins. That changes the state of stress, and the deformation mechanisms, in fact, change as a response to, if in fact the rain had come from the north, the plateau almost certainly would look a lot different than it does. And lastly, and this is a puzzle that when Western geologists first arrived, the French started arriving in 1981, 82, the big puzzle was, well, this is the textbook example of a convergent orogeny, right? And, this model, in fact, has been published before a Western geologist steps into southern Tibet. And the weird thing is that although pre-collisional Cretaceous and older rocks in southern Tibet are highly deformed, there is a widespread ignimbrite flare-up at around 60 million years, and everywhere in southern Tibet, those rocks are flat-lying and undeformed, essentially. So, in fact, the antithesis of this, that in fact the only part of Tibet that doesn't seem to have deformed is the part that was adjacent to the collision. Okay, so we're going to cover these models. Let's start with what I already mentioned, the idea of what became known as Continental Escape. Paul hates that term, refers to it as a lateral extrusion model. But here's the idea, that if you look at this map view of Southeast Asia, you see India, the Himalayas, Tibet, and then Indochina, Sundaland here, which in fact is bounded to the north by a now deformed a fault that Paul argued was the equivalent of one of those slices in the analog model, right? That here's Sundaland, and here's the Kunlun fault up here, and here's the Himalaya. So roughly speaking, his argument is that Sundaland used to be here, okay? And as
I can't really tell what that image is about, the previous one.
India hit, it didn't produce uniform distributed deformation starting by building a plateau in the south and having it propagate north. Instead, because of this, essentially stress-free boundary over to the east, as India moved forward, Sundaland basically got pushed out of the way, and it wasn't until you made hard collision until that was finished that you began to lift up the Tibet and the Himalaya. One of the earliest criticisms of the model was the fact that you see this has to have a left lateral sense of displacement, right? Sundaland has to be moving here relative along the Red River Fault, and the fact is the fault is active, but in a right lateral sense. But nonetheless, Paul's hypothesis.
It would help if I was paying attention, I said. I muted myself.
Was, look, we have the seafloor stripes out here in the South China Sea. The South China Sea ridge here is basically marking, it's showing you a pull-apart basin. It is, in fact, the pull-apart connected, okay, in this plate system, the termination of the Red River Fault going into this more distributed deformation in central Tibet. So, in fact, as India's moved northward, we basically ripped ourselves some new oceanic crust between 34 and 16 million years. So Paul's...
Let me just Google that. Do-do-do. Do-do-do. Do-do-do-do-do. I wish this stuff was all just freely accessible. It literally limits. These things smell so nice. For sure. They've been used in puja. Puja, I think that's called. I don't know about that kind of puja. Maybe though. Okay. I'll just go home. There's probably something interesting there relating to when the Earth exploded. Could it have been like producing a slab of oceanic crust underneath Australia, which then like tilted when the Earth supernovaed, essentially pushing it this way? So even though this is older oceanic crust, it's just like it was underneath Australia, and then it moved Australia away to like come to the surface as this section. Because this is really way before when the supernova occurred, which is so anomalous. I know people who are hearing me for the first time. Like, what? It's just the fact of the matter. The Earth supernovaed, and this was a major part of the process. This is not true. It's the relative age, but not the absolute age. Because it all occurred rapidly when the Earth supernovaed, which was radioactively decaying, and then it became in a new steady state again, basically. We're very much in a steady state relative to when the Earth underwent expansion from a single landmass. And part of the process was, it seems that it fractured this way, came across here, and I guess it just like, maybe it went under-ish Australia. Like it didn't really, like this is crazy. I also wonder if the moon was separated in the supernova. Like it was part of Earth, because the Earth would have been really small compared to Venus if it was just these continents. But it may be that like I'm not understanding. There was a chunk on the surface somewhere that like could have been a chunk that was reshaped into the moon as we see it, and just like folded in on itself, and in so doing all the particles within it just kept decaying and supernovaing, creating all these craters on the edge on this crust, and then it took a new shape where it's spherical and stable, And the crater stopped basically, and here we are with a moon that was maybe, I mean, composed of some emitted actual Earth crust when the Earth expanded. It is a possibility, although I've generally just claimed and believe that it appears that it looks like it would have fit together perfectly fine on a sphere, so to add something else in there, I'm not sure where the moon would have been. It would have had to be somewhere in the confusion of it all, like somewhere. So maybe in this region there's some missing components of the crust that are literally like how big is the surface area of Earth? 200 million. Moon. That's a big chunk. That's a big chunk. Imagine like that chunk was like here. I mean, it could fit in the Pacific there. Generally. Like there could be, or even maybe have been emitted from like off the coast here also. Or something. I don't know why. Just a side tangent. 5 United States equals 1 moon. I mean, it's not that big. It could have happened. And it's possible that, like, it doesn't take quite as much surface area because, like, the layers, like, let's say it's 10 layers and, like, it's a single plane that just got shot out into space and starts to fold in, like, from the fold, it just folds in along the edges and starts to crack, but like it's still a single system, and it just starts to go through all these processes where the particles are literally rapidly decaying to keep the overall system stable. So I mean, I just heard the other day, this is crazy, yesterday, the moon 4 hours may have formed the moon in mere hours. 4 hours? Wait, I'm not sure if that's it. But collision may have formed the moon in only hours. Like, what? That is catastrophism. That is not uniformitarianism. Catastrophism. You know, major upheavals where sudden spontaneous changes occur. That's what this suggests. There was a sudden change, and the fact that we think it to be the same age, maybe it is the same age, and maybe it does have like things on the surface that are somewhat preserved. I mean, it would have been undergoing massive radioactive decay and upheaval, so maybe that was destroyed largely. But maybe there are things on the surface of the moon that are from before the Earth expanded, because it was part of the Earth. I don't know. I've supposed. And it's kind of similar to this, where it emitted a new system, like made a positive membrane, cathode, membrane, anode. And this is interesting. Maybe I can find it. Pardon me. Maybe this one. I was trying to find out here it is. Dendrite growth. So mind you, I was saying previously, the Himalayas are dendrites of a shallogram. So these are like interlocking dendrites in the same way as this is on the mountain chain of the Himalayas. Okay, so there's that kind of thing going on. And, is this where I was? Yeah, so, oh yeah, back to this one. And look at this. What is this? Wait, how come I can't view it as easily? In short, it says anode over here, and then dendrites branching towards a cathode. Like, how crazy is that? That there's... Because I essentially said, before I even saw this, I was like, this looks like an anode because it's like a negative. It's a missing thing. So, oops, I don't know what just happened. It's missing particles because the particle underneath here is supernova, sending out a wave underneath this crust that then was able to hit a sufficient resistance at the Indian Craton region, which then causes an uplift and an arc from the supernova, creating literally a voidish negative region with a positive cathode type region, and then a membrane type region, and literally that's how the dendrites form is like oh my god, towards the cathode, essentially, like this. So it's like India then contains some like cathode positive charge particle, that the particle that was underneath underneath Tibetan plateau, this region underneath here, this particle behaved as like a negative particle towards and functionally gave energy to this system through the mountain chain, propagating energy through this. And now there's literally a battery here because the system's not stable like the Earth was once here. And then it literally supernovaed in the Earth expanding. And it sent out maybe a arc that became the moon, even though in that instance it would be the cathode here. Point being, possible the moon had a similar relationship where there was no anode cathode of the Earth and the moon. There was only the one system of the Earth that didn't have yet supernovaed, but it wasn't that much smaller. It was more Venus-like. Just some thoughts. Maybe somewhat smaller than... because the expanding Earth model basically is like a 50% radius. It's a pretty small Earth to a point where it's like, how did Venus become that? Because that's how I see things. I'm like, why is it so small? Like, Venus is similar to this Earth. So why is pre-expansion Earth so small? It must, like, I know that theoretically Mercury supernovaed and sent a shockwave through the planet Venus, causing it to become Earth and causing Mercury then to become Venus. And that's maybe that like caused the planet to lose some material and shrunk. I was thinking, but like, that doesn't seem that like explanatory, but like a more when the Earth expanded kind of explanation maybe is more reasonable.
Paul's hypothesis actually is testable. Okay, which, frankly, when you look at the the scale of things, all we can really do is go on fishing trips, go and make some observations. So we're really still in the exploratory phase. But here was a nicely posed problem, because if his hypothesis is or some successful tests would be, even though it's right lateral today, it has to have been left lateral during this period. We can determine that there's been about 700 kilometers of opening, so we expect 700 kilometers slip along the left lateral slip along it. And if it's feasible, we should have evidence that this shear zone was active between about 34 and 16 million years. Okay?
Does that strike slip fault really line up with the, is it one of the transform faults on the strike zone?
At this scale, yeah. In detail, this is a lot messier than and that's also been the subject of some. There's a lot of this thing hasn't been active for 16 million years, so there's a lot of sediment bearing features. But by and large, I mean the overall the 0th order, as you'll see, predictions have been borne out. This is a lot of information crammed onto one slide. The first thing I want to point out is, here's Hanoi. Kunming would be about here. Here's Kunming. And there's a series of massifs, the Dainu Convoy in Vietnam, the Ilo Shan, okay, the Denseng Shan and the Zulong Shan. These are essentially fossil remains, in fact, and if you look at them in detail, of a left lateral slip. Okay, the kinematic indicators are that despite the fact that the
Oh my god, and the vortex.
active strike slip fault with a normal component is right lateral. This has probably only been going on for about the last 8 million years or so.
This just looks like a freaking image of Venus, or Jupiter, the surface of Jupiter. Like, imagine Jupiter froze, and we got to look at it as a and say like 0.1 millimeter. It look like that. That's what it looks like to me. Like there were flows in each direction, creating a spiral that literally has little.
And that the dominant deformation mechanism in these really highly deformed gneisses was left lateral. There was a very fortunate circumstance that has allowed thermochronology, talked about the other day, to address this question of the timing, and that is that if you look at the polar rotation from the South China Sea, and I'll point out that the Red River Fault, in fact, you see this bend? This fault here is actually offset. If you restore that, what you find is the polar rotation isn't exactly coincident with the Red River Fault. It actually predicts, because of overlap, I think, let's see, the polar rotation looks like this relative to the fault. So it's predicting that there would be transpression up here and transtension down here. And indeed, the Ilo Shan, the shear zone in the south, in fact, has been extended to the point where the fabric in the rock is rotated almost horizontal. So what you're looking at here is the timing in kilometers north of Hanoi of the passage of this transition from transpression to transtension, because in fact what we can see in the argon, in the potassium feldspar multi-domain H spectra, is we can see the onset of extension. And if you plot this for any particular isotherm, let's take the 200 degrees, in fact this transition is propagating along the fault at about 4 centimeters a year. That's what you'd predict from the slip rate from the South China seafloor stripe. So that works pretty well. Only goes back, we lose the information at about 25 million years, but in fact, we can go in with an ion microprobe and use uranium, thorium, lead dating of garnets that are distributed in high-grade rocks in the Dainu Convoy and the Iloshan. And what we find is garnets that have grown under left lateral deformation. And the age of these inclusions that were forming as simultaneous with the garnet formation are between about 25 and 32, 33 million years old. So we have evidence in the rock record of left lateral slip between, say, 32, 33 billion years and 25. At 25 million years, we have the argon record picks up until about 16, 17 million years. So what do we got? We've got evidence, the same timing between about 32 and 17 million years, same magnitude of slip, same magnitude of offset from paleomag. Now it says around 700 kilometers. You can imagine the errors are large, but they're within uncertainty of the amount that you predict from the seafloor stripes in the South China Sea, and that in fact, when this thing was active between 32 and 16 million years, it was in a left lateral sense. So I'd have to say that this is the one well-posed problem that's been addressed, and because of the success of this model, although the partisans with the thin viscous sheet model haven't exactly heralded its triumph, it's in fact led to a more generalized model, which is that it isn't just Indochina that's experienced this mixture of trans-tensional impressional faulting coupled with intercontinental subduction. Paul generalized this in 2002 to the entire plateau. And his argument, then, we're looking south to north. Here's the Himalaya in India. And what he argues essentially is that same mechanism, lateral extrusion, coupled with intercontinental subduction and production of calc-alkaline magnets, which you do see on the plateau, is what led to the growth of the plateau, again propagating from south to north. And as I mentioned earlier, actually, as we look in detail, what we find is that the earliest evidence of crustal thickening isn't right at the suture, but rather it's in the Kunlun Shan, the Nanshan, and so on further north. So it's a little puzzling. Okay, India hits here, and the first thing that happened is a mountain range goes up here. Okay, so we really don't understand some aspects of this. Yeah, Alan.
So those level square columns don't really balance with the crust. So it's all of that already.
You mean because we have the different.
This looks like maybe after it has some like returning, like as it's no longer able to reach up here, it's dwindling, and it's only able to reach up here, so maybe it penetrates through some sort of like dendrite feature again, and then channels into some region, and then it's no longer able to make it even there, and it goes through some other region, although it's kind of going backward. I'm not sure still. I feel like it would still maybe go like that, but maybe not. And then again, as it's retreating, so maybe it is kind of retreating because this says to present. To present? I think that's the Himalayas itself. But that would not really mesh well with the retreating these things, although
Different thicknesses of mantle.
You've got these slabs going down, and so your line length on the top of the certain mantle was about roughly twice or 3 times the.
Okay, so that thickness doesn't balance with what was carried into it. Well, I'm not. Well, I'm not going to. Of course, there's all kinds. There's clearly movement for a lot of erosion from the top. But I'm sorry, I actually failed to mention this. That in fact, Paul's argument as to why the plateau is so Tibet is flatter than Kansas. Okay? Literally, there's more tilt to the state of Kansas than there is across the plateau. His argument is that this transpressional faulting essentially cuts off drainage, and Tibet is flat because it's being internally drained. So where you see these thrust systems, he's not actually proposing that material's transported out. It's basically, it's getting filled into these basins, and that's what's keeping Tibet level. I'm not a big fan of this model, despite the fact that I think he's nailed it with.
Yeah, no, I don't know. That's real interesting, though. Tibet is flatter than Kansas. Where is Tibet? This? He must be talking about some, like, right here or something. Up here, maybe? I guess here. This is not that flat. I don't know. Like, Kansas isn't like that, is it? Like, what the? Like this? I'm not sure where exactly. It's flatter than Kansas, though. If there is some flatness before the mountain terrain.
Sunderland's extrusion, and the principal reason is simply there is no clear evidence of northward propagation, and indeed, what evidence there is suggests otherwise. Okay, now a little tutorial before.
Okay, okay, I think I understand. Is that these were kind of based on the assumption that India's colliding into. Essentially, we've established that there's this, but like for sure, India's colliding in Asia, so it's producing what it clearly should be doing if that's what's happening. It's doing it just over at the plateau. That's what's going on, and then there's this other one afterwards.
Keeping Tibet level. I'm not a big fan of this model, despite the fact that I think he's nailed it with Sunderland's extrusion, and the principal reason is simply there is no clear evidence of northward propagation.
No clear evidence.
And indeed, what evidence there is suggests otherwise. Okay, now a little tutorial. Before we take that, that was a relatively straightforward issue. It gets complicated now, and you need to know a little bit about the geology of the Himalaya. Okay, here's the gangetic plain down here, series of thrust faults. This is the suture, separates true Asian rocks from rocks of Indian affinity. You only actually see the suture in a couple of locations. It's already gone. When people argue that, as some do, that plate tectonics didn't begin until 1 billion years ago on the planet because you don't see ophiolites, rocks much older than that, or they're extremely rare, I point out that here you have 3,000 kilometers of collision front, and we actually only see ophiolite in about 3%. So even before this origin stopped, the ophiolite.
Okay, so just because there's ophiolites, we describe them as ophiolites because they are there, but they're only actually there in 3%. Okay.
ophiolites were either, buried or eroded or some other way terminated. So I don't see that as a particularly strong argument. Okay, there's a bunch of different rock packages, and I'm going to
Go back and just make sure.
see the suture in a couple of locations. It's already gone. When people argue that, as some do, that plate tectonics didn't begin until 1 billion years ago on the planet because you don't see ophiolites, rocks much older than that, or they're extremely rare. I point out that here you have 3,000 kilometers of collision front, and we actually only see ophiolite in about 3%. So even before this origin stopped, the ophiolites were either, buried or eroded or some other way terminated. So I don't see that as a particularly strong argument. Okay, there's a bunch of different rock packages, and I'm going to put this up here so you guys have a, have a quick reference from south to north. So here's the crest of the high Himalaya. Okay, this is the Indus Tsongpo suture. So this is the suture here between Indian rocks and Asian rocks. Yes? Okay, okay, so let's, okay, this is the Indus Tsongpo suture, okay? This is a,
Oh, don't judge me.
does that work? Black works? I was actually going to use black for the, let me do this for these structures. This feature here is the South Tibetan detachment, or the STD. Okay, and this is a curious feature.
Indus Tsongpo suture. Okay, there we go.
And this is a
Oh, so it's even before the plateau, or what? I don't know.
curious feature, okay? The STD, again, despite the fact that this is the textbook compressional origin,
I just want to see that map more clearly. This suture zone. Yeah, so he's saying in the region where there are ophiolites, there's only actually 3%, or no. Or wait, no, Tethys, Himalaya, that's this one. Maybe he was just saying only 3% ophiolites in that one.
there is a normal fault develops midway between collision and present day. And it has the down to the north sense. And of course, for the most part, the explanation is you build a mountain range up high enough, in fact, it becomes gravitationally unstable, and this is basically just, sliding off the roof of the world here. There's a fault here called the main central thrust, okay, and this is the big guy. This is the one here that really is responsible for 85% or something like that of crustal thickening in the. And then the guy down here is the main boundary front thrust. And actually, there's another one, the main frontal thrust. We don't need to worry about that. What I wanted to do, though, is to then define these rock packages. As you look at the Himalaya, between the South Tibetan detachment and the suture, this is the Tethyan Himalayan series. So I'm going to call that the THS, okay? That's the Tethys. And that's basically, the goo that formed on the leading edge of India prior to its collision. So this is the deep sea sediment, for the most part, on the leading edge of India that was the first to, in fact, experience interaction with the marginal southern Asia. Okay. Between the MCT and the STD, there's the greater Himalayan sequence, and this is in yellow. And these are very high-grade rocks. These are amphibolite and then locally granulite grade rocks. This is, again, a more proximal sedimentary package from India that's been stacked up.
Oh, fuck. God damn it. Okay, I just need to write this. I've probably written it, but certainly seen it, but okay.
Main frontal thrust, we don't need to worry about that. What I wanted to do, though, is to then define for 85% or something like that of crustal thickening in the, and then the guy down here is the main boundary front thrust, and actually there's another one, the main frontal thrust. We don't need to worry about that. What I wanted to do, though, is to then define these rock packages. As you look at the Himalaya, between the South Tibetan Detachment and the suture, this is the Tethyan Himalayan series. So I'm going to call that the THS, okay? That's the Tethys. And that's basically, the goo that formed on the leading edge of India prior to its collision. So this is the deep sea sediment, for the most part, on the leading edge of India that was the first to, in fact, experience interaction with the margin of Southern Asia. Okay? Between the MCT and the STD, there's the greater Himalayan sequence, and this is in yellow. And these are very high-grade rocks. These are amphibolite and then locally granulite grade rocks. This is, again, a more proximal sedimentary package from India that's been stacked up to make the Himalaya. Unfortunately, it's also, what do we call it here? Here we're, in fact, it's called the GHC, the Greater Himalayan Crystallines, also known as the higher Himalayan series. Okay, so maybe I'll put that in. Higher Himalayan. Okay. And then the lesser Himalaya, LHS, that's these rocks in green, and then it really doesn't matter what's down here. So we can think of this as Tibet across the suture, and then these various distinctive rock packages. Now, if you look at the Himalaya, these blobs in red are leucogranites. They're these these are granites that appear to have melted, not from a good Andean type of protolith, but rather they appear to, in fact, have melted from shaly rocks from perluminous origin. And there's a belt that runs right along the crest of the high Himalaya. So this would be the snow-capped peaks you saw in the first slide. And there's some biggies. There's Manaslu there. And to the north, about 60, 80 kilometers, there's a second belt called the North Himalayan Granites. Okay? So that's the first of these petrogenetic puzzles of the Himalaya. What's the origin of this belt? And it's going to have to be a pretty... We could imagine that the answer to this question is pretty specific, because I frankly challenge any of you to tell me where else on the planet is preserved two parallel belts of perluminous rocks like this. So this is kind of unique. Okay, let's have...
Two parallel belts of perluminous rock.
Belt, and it's going to have to be a pretty... We could imagine that the answer to this question is pretty specific, because I frankly challenge... They appear to, in fact, have melted from shaly rocks from perluminous origin. And there's a belt that runs right along the crest of the high Himalaya. So this would be the snow-capped peaks you saw in the first slide. And there's some biggies. There's Manaslu there. And to the north, about 60, 80 kilometers, there's a second belt called the North Himalayan Granites. Okay? So that's the first of these petrogenetic puzzles of the Himalaya. What's
Two.
what's the origin of this belt? And it's going to have to be a pretty, we could imagine that the answer to this question is pretty specific, because I frankly challenge any of you to tell me where else on the planet is preserved two parallel belts of perluminous rocks like this. So this is kind of unique. Okay, let's have.
Real quick, what are in general cross sections?
Two parallel belts. It's hard to say where.
First slide, and there's some biggies. There's Manaslu there. And to the north, about 60, 80 kilometers, there's a second belt called the North Himalayan Granites.
Granitoids. Down the do. Do 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 do. Meow meow meow. Meow meow meow. Himalaya is considered as. I didn't realize it was called the Himalaya until I started looking into it. Now I've come across that pretty regularly. It's considered as a typical example of continent-continent collision between India and Eurasian plates during the Cenozoic time. What was I looking at this for? Oh yeah, the granites. Like to see. Oh. Ages of North Trans-Himalayan batholith, much of which occurred at it's literally at specific points. Like this is when Deccan traps and Chicxulub and so on happened, and then it began a process, a chain reaction of other things. So it's not like they're exactly the same time, but like this is, I'm pretty sure, like Permian. And then the 500-ish ones come across that kind of time frame. Totally different time frame for this one. The North Himalayan ones were granite belts. The North Himalayan granite belts were formed early on in the process. I wonder if like there's some fucking something in Hindu scripture that describes some attack on this region that led to this at the beginning, and Dwarka was not again the only, it wasn't the only thing going on was the attack on Dwarka. I don't believe that's the case. So it's quite possible there's just other inputs involved that I'm not really accounting for that are significant, like something going down here where it was attacked with some weapon that. But to me, it seems like it's from water pressing on the top. Makes most sense because of the imbalanced direction of the propagation of the energy. Okay. I don't see any pictures that are like this. Is really informative to see. A lot of late. This is like post-supernova late formations only in the high Himalayas. Whereas, I wonder if some of these are in places intermixed and it's hard to tell what. Like, that's weird. That's very strange. What? What? What is this? Oh dear. It's like all this data gets ignored when summarizing, in essence, what is happening. Like, these don't matter. The true thing is there was something around 500 million, and around this time. That's what I've mostly heard in the presentations. But this shows a lot of readings that I've not heard us even mention that there is such a spectrum of ages that goes back to 2 billion. Like, are these also shaped? I'm not quite sure why those wouldn't be relevant, or if they're just considered to have been before the actual mountain building event, so that the ages don't actually matter. So they're kind of dismissed, like, knowingly, like, in an unconcerned kind of way, rather than sweeping under the rug, just like, no, it's fine.
Okay. So that's the first of these petrogenetic puzzles of the Himalaya. What's the origin of this belt? And it's going to have to be a pretty. We could imagine that the answer to this question is pretty specific, because I frankly challenge any of you to tell me where else on the planet is preserved two parallel belts of perluminous rocks like this. So this is kind of unique. Okay, let's have.
What are the general cross-sections of the Himalayas?
Really, more so than just the shallogram itself. I wonder if that is more like when it comes out the sides, maybe like this. Sometimes it's got like the gold seeping out the sides. Maybe it's more like that's what the granite are in those instances, is like this. Even in a dendrite type of way, where maybe the mountain chain is more generally like this, but sometimes having intrusions coming out, some pathway, some channel. don't know if I'm using that word right. Pardon me as I try to use geological terms. Intrusions.
Yeah, these are basically, these are, as I say, more proximal sedimentary package. The GHS is characterized, if you will, from a geochemist's point of view. Epsilon neodymium here is about 14. Here, it's largely dirty sandstones, not very, very. There's some calc-silicate and some Pan-African igneous rock, but that's about it. Basically, dirty quartzite. Okay, LHS. There are shaly rocks, carbonate rocks in here. Epsilon neodymium is. Sorry, I said 14. I meant minus 14. Here, about minus 24. So in a sense, these are implicitly younger sediments than this package. So if here's India, the Tethys would have been here. There would have then been this shelf. Here's the greater Himalayan protolith, and then the lesser Himalayan, and these things have now been stacked up as a result of the collision and subsequent convergence. Good, thanks. Okay, so part of understanding this leucogranite belt problem is the fact that it's only been relatively recently, about the last 10, 12 years, that we've actually been able to determine the age relations, because these perluminous, these S-type rocks, they don't like to dissolve the minerals that we love to use to date the age of granites. For example, uranium, thorium, lead dating of zircon or monazite, things like this. The solubility of monazite or zircon, these accessory phases, in crustal melts is vanishingly small. So the problem is, back in the old days when you used to like to collect a gram of zircon and then dissolve it and put it in your mass spectrometer, imagine this case here. Here's a monazite grain from Manaslu. That's, in fact, I think I pointed out, that's this guy right here. And he is 22 million years old, okay? So now we have a device, an ion microprobe. I mentioned the other day, we can go in and you can see the problem. There's a core that goes back to, in fact, Pan-African ages. If I were to dissolve this...
There's too many numbers on it, dude. Can't say it.
What's the age I'd get? I'll give 58 million years with very high precision, okay? But it wasn't until we were able to do in situ dating that we recognized that the high Himalayan leucogranites, the ones that are along the snowy crest, they're 24 to 19. Those ones, the North Himalayan leucogranites, the belt further north, they can be, little bits can get that old, but for the most part, they're younger. These appear to be virtually minimum melts, or at least derived from muscovite dehydration, melting. They're syntectonic dikes and sills. These are more like diapiric plutons. So let me show you sort of the artist's conception here. So the high Himalayan leucogranites, these are sort of dikes and sills. They're deformed. They are adjacent to, above and below the South Tibetan detachment system, mostly below. And here's the sort of more diapiric, seemingly higher temperature. Why higher temperature? Because they have less inheritance. The hotter a magma, the more accessory mineral you can dissolve. Okay, we're still calling them the greater Himalayan crystallines here in yellow. Now this also shows the second petrological feature, which is the so-called classic inverted metamorphism. Let's actually blow this up. Okay, so there's the South Tibetan detachment. Here's the main central thrust. Here's the and you'll notice that as you, in fact, let's blow this area up here. As you go from seemingly structurally low positions, right, and you walk, up section in the Himalaya, you go from zeolite grade to chlorite grade to biotite grade to garnet grade. Okay, you see what's happening? All of you have done undergraduate petrology, I suspect. We're going from essentially dirt grade rocks up to, second sillimanite isograd. And this was, English geologists recognized this in the 1870s and were puzzled by it. And interesting that in those days, a rock that was, at amphibolite or granulite grade was Archean. Okay, high-grade rock was an old rock, so that's what was puzzling to them, which is you had, old rocks on top of young rocks. Well, that, obviously hasn't stood the test of time, but nonetheless, it's plain. In the 1970s, 1980s, first actually inspired by Patrick Lefort and then quantitatively by Phil England and Peter Molnar, they focused on the fact that the main central thrust, which I say is the locus of most of the action in the Himalaya, is responsible, in fact, for creating heat during slip that would have flowed laterally into these lower grade downgoing rocks. So that inspired a whole bunch of models. Is that clear? Anybody? They focused on the fact that the main central thrust, which I say is the locus of most of the action in the Himalaya, is responsible, in fact, for creating heat during slip that would have flowed laterally into these lower grade downgoing rocks. So that inspired a whole bunch of models. Is that clear? Anybody got any questions about that? Yeah.
I think another reason the British interpret that is because you have intelligence series on top of those, like the Everest, you have limestone, fossils.
I'm not sure they knew that in 1870.
And so they interpreted that as a which was an enigma until we got the first 40 million years.
Yeah, actually in Mussoorie, where this was first observed, there would have been no access to that. I think that's an observation that would have come later. Yeah.
So I have a question. Just
Yeah.
Can you go back to the previous slide? So is the RZT the same thing?
Sorry, yes, this is the ITS, right. You'll notice, as I mentioned, that the ophiolite's pretty much gone in most locations. This is the Renbuzherang thrust. This is a back thrust that basically has, chewed up evidence of the original suture. So this this is between maybe about 15 and 9 million years. This motion here has basically, and in fact, this is the Gangdesi thrust. Again, you only see the Gangdesi thrust in the whole collision zone exposed over about 100, 120 kilometers. And simply because the RZT backs off there and this thing gets exposed to the surface. And this was important in thickening southern Tibet. Yeah. Sorry, yeah, so RZT, this slide. And actually also it's now called the Great Counter Thrust because that was in fact the original description of that back thrust from Adolfo Ganzer's work in the 1920s and 30s. Yeah.
Which one's the leucogranites?
These are leucogranites and these are leucogranites. They're all leucogranites.
Which one's the high?
Sorry, these are the North Himalayan. These are the High Himalayan. Yeah. Yeah, I get your point. Thank you. Anything else? Yeah.
You mentioned that lower Crustal flow model. Is that the
I-
CHS that's flowing out of that particular rocks?
No. We're going to talk about this in detail, and I better get moving, in fact. This, in fact, the thought is that the greater Himalayan sequence, these high-grade rocks, in fact, were once molten Tibetan lower crust. And I really did need to boot this. So, yeah. Okay. The problem is when we did develop these in situ dating methods, what we found is, it's sure, that the rocks in the hanging wall, these were all deformed and melted 22, 24, 19, 23 million years. But the recrystallization down here, in fact, we have excellent evidence. For example, here's a garnet that we know from, petrological PT methodology, grew at a depth of about 25 to 30 kilometers. But in fact, the inclusions that grew synchronous with that garnet formation, they're 8, 7, 6, 5, 4, even 3 million years old. So this was a gigantic red herring, right? It sure looked for the world like, oh, hot rocks, fault, cold rocks, frictional heating, lateral flow. But in fact, the recrystallization down here has nothing to do. These rocks were dead cold when the recrystallization occurred in the footwall. Okay. Okay, so now let's, I showed you these models earlier. There's 4 types of models for the inverted metamorphism in Anatexis. I mentioned to you the Lefort model, which focused on The MCT, basically the hot iron model, you bring hot rocks, you have substantial shear heating on the MCT, and you're going to create the sawtooth geotherm adjacent to fault. Heat will flow to the footwall, and that's why the metamorphic grade decreases. Another one, Royden and her colleagues developed, was that here's the main central thrust. Basically, you have accretion, and actually that's a pretty good idea, that you have rocks from the lower plate accreting into the upper plate, and because these lesser Himalayan rocks are very radioactive, over time, over tens of millions of years, you can melt those rocks because of the high. And I'm going to show you. Now, here's Peter Bird's original model.
I was just thinking that it does kind of fit with the supernova still. I mentioned this in a previous video, that's why I just didn't say anything. But where he said the heating, like the further north ones experience heat, and then the southern ones later experienced heat. Seems fine with the supernova still. Everything so far is fine with the supernova model that I've been mentioning thus far in my Himalayan analysis.
Model, Bird 78. This is his idea was, oh, look, you have these North Himalayan granites and these high Himalayan granites simply because the mantle lithosphere, what did he call it? Delaminated, okay? And the asthenosphere came up to the base of the crust and produced this melting. I'm not going to talk about this further. This, in fact, is unlikely to create perluminous melts, and we know, as Wang Ping will tell you next week, this is inconsistent with the seismic imaging. The Nelson model, Alan's already alluded to this. Doug Nelson, as a result of a seismic survey in southern Tibet, proposed that the greater Himalayan sequence, here's the STD, here's the MCT, that's these guys here, the greater Himalayan sequence, actually originated as partially molten rocks and basically got squeezed out like a watermelon might between your fingers. And we're going to talk a lot about that because that's been very influential. Another is the Lafore model, which I'll mention, kind of died a natural death when Nigel Harris and his co-workers pointed out that the chemistry of these high Himalayan leucogranite rocks is absolutely inconsistent with their formation in water-saturated melting. The Lafore model, you take these hydrous, these water-rich, low-grade rocks, you thrust them with high degree of shear heating. The MCT, hot hanging wall rocks, the heat gets transferred, you dehydrate, and water gets fluxed across, and it causes minimum melting in the hanging wall, except that, in fact, these are all produced essentially by fluid-absent reactions. So Nigel's point is like, well, wait a minute, what about good old decompression melting? If you have the STD, if you have this normal fault, you can take a rock, right, that's initially right above the solidus, drop 10, 15 kilometers off it, produce some melt. That's how you're going to. And we're going to come back and talk about these in turn. Type 4, inverted metamorphism, is due to the transposition of right way up metamorphic sequences. You can do it ductily. Mike borrowed this from an Italian worker. Here's Mary Hubbard's model, which inspired, led to, our model I'm going to introduce you to a little later, and that is simply that it's all just it's a terrible mistake. It's a red herring that you had a single right way up metamorphic sequence, and what's happened is it's been juxtaposed, the strain so high that the isograds have been rotated essentially into parallelism with the shear zone boundary. So as you walk through the Himalaya today, it sure looks like you're going from low grade to high grade, and you are, but it's simply because you've got this tectonically accordioned section through the shear zone. And to some degree, this is actually, and then actually in the mid-90s, Jameson Beaumont pointing out that maybe this is because, in fact, this isn't just fault bend fold tectonics. Maybe there's fluid motion allowing material that starts at different positions to flow and be juxtaposed. And this ultimately led to the the channel flow model. I'm going to talk a lot about if I don't, if I can get through this quick. Okay, so again, the LaFour model, not successful because it assumes that inverted metamorphism and hanging wall in Texas are temporally related, and they're not. This was hot 24 million years ago. This didn't recrystallize until 8 to 3. That's dead cold at that time.
Okay, now I picked up on what I should have been picking up on, which is that that's not dead cold at that time. You're actually, it's literally thousands of years ago. Post-radioactive decay of the planet when it's supernovaed. So, I mean, and time was rapidly passing during the radioactive decay of the planet in terms of our current rate of radioactive decay when we look back at radioactive decay during this process. It was extremely rapid, like 1 million years per day. So, you know, it really wasn't that far of a difference in that fact of the matter. So actually, that might be a piece of evidence that the time wasn't that long, because it further supports it. Because that's probably what I was thinking that initially. I wasn't quite understanding what he was saying. I was like, maybe it just like transferred the heat, especially towards the cathode, like the heat into the object of the, that it was moving the energy flow towards. Maybe the exchange of energy caused the heat exchange into India that basically ended by the carved conduit connector having just exchanging heat, and then at the way it did it, plausible.
Quantitative efforts to model this. In fact, England and Molnar wrote a sequence of, I think, 4 papers over about 15 years in order to make it work, because this is the worst place in the world to make granites, right? You've taken these ice cold lower plate rocks and you're refrigerating so they ended up having, in order to meet the observation, they had to put 10 kilobars of shear strength on the rocks as they melted. And it's a wonderful paper, actually. I'd recommend it to you because, again, this is sort of the long-standing tension between geophysicists and geologists. Because this paper, which actually makes what I think is an absolutely preposterous suggestion that these rocks could have 10 kilobars of strength at Antarctic temperatures, because the introduction has this...
Preposterous, you say. Tell me more. Is that this one? I'm not sure. The Fort Himalayas, Molnar in England, 1993. Yeah, sure. 1990, 93. Mantle Dynamics. Abstracts. Download PDF. You might want me to log in. Or convective removal of lower lithosphere beneath the Tibetan plateau from the supernova of the particle. can account for rapid increase in the mean elevation of the Tibetan plateau. What? Damn. Such an uplift account for increase in the mean elevation of 1,000 meters or more. Literally shallogram convective removal of lower lithosphere. Shallogram. Such an uplift seems to be required by abrupt tectonic and environmental changes in Asia and the Indian Ocean in the late Cenozoic time. The composition of basaltic volcanism in northern Tibet, which apparently began at about 13 million years, implies melting of lithosphere, not asthenosphere. Which one is this one? Upper layer of the mantle. Whereas the other one is crust. Still. Yes. Melting of the lithosphere, not asthenosphere. Most plausible mechanism for rapid heat transfer to the mid-lithosphere is by convective removal of deeper lithosphere. Its replacement by hotter asthenosphere. Plateau underwent an appreciable increase in elevation at that time. Isostatic response to crustal thickening. Although I don't know if that I agree with this at all, because I don't. Just the mechanism of India colliding into Asia is not true. So get it out of there, guys. Explain it without it. It's called the expanding Earth model. We need more models from the expanding Earth model branching into other things. It's kind of like once you have an established model, you can move on from the thing. So like that's kind of what we do, but sometimes we gotta go back. But you know, like if there's a model trying to be proposed, like expanding Earth, like it tends to just kind of sit there until it's accepted. So like it doesn't build is in the same way where like, okay, move on from, okay, the Earth did expand, now what? Like it's just people constantly trying to get people to look at that the Earth did expand. I'm getting stuck in that, like the theory of everything. Just trying to propagate it. But there's so much more. So much more. And it's only able to be found by looking. Okay. Such as removal of relatively cold, dense lower lithosphere must have caused a supplemental uplift of the surface, folding and faulting. This strongly corroborates what I've said so far. from an amount too small to the full to one. Tibetan Plateau provides a heat source at mid-latitudes that should oppose classical Hadley circulation between the equator and temperate latitudes. Like a supernova. Can we just look into this? Axisymmetric heating. No dependence on longitude of an atmosphere without dissipation. Theoretical analysis. Can drive a much stronger meridional monsoon-like circulation than such a source centered on the equator, but only if heating exceeds a threshold whose level increases with the latitude of the heat source. Because heating of the atmosphere over Tibet should increase monotonically with elevation of the plateau, a modest uplift of Tibet, already of substantial extent and height, might have been sufficient to exceed a threshold necessary for a strong monsoon. Interesting. The virtual simultaneity of these phenomena suggests that uplift was rapid. Moreover, nearly simultaneously with the late Miocene strengthening of the monsoon, the calcite compensation depths in the oceans dropped. Plants using the relatively efficient C4 pathway. Oh my god. These are probably fossils that are not fossils that they're referring to. Plants in the ocean? You mean fossils that are not fossils? Is that what you're referring to? That were also influenced by the supernova? I see. I see. It's just so many subjects to get to know in like depth.
They're very much the English schoolmaster, sort of like, now you stupid geologists, we're going to tell you this one more time, okay? Oh, they weren't talking to me. So let's see. Oh, assumes water-saturated melting. And again, that's absolutely clear that 98% of these things are vapor absent. And then, again, it just required absurdly high shear stress. So, in fact, when we finally recognized that these two things, the inverted metamorphism and the anticycles, weren't temporally related, that just made it all simple. The Royden Model actually kind of took leadership. This is a good idea. Only in this case, it doesn't work. I mean, her model, because of its simplicity, predicts that there should be, 5 more Bay of Bengal sedimentary deposits. But again, you could modify this model to relax that problem. It predicts the Himalayan exposure too deep. Again, modifying the model would fix that. I won't even tell you what that is. Inconsistent, yeah, but mostly important is, though the footwall rocks, as I mentioned to you, they're isotopically. Here's the lesser Himalaya, here's the higher Himalaya, okay? You don't keep the higher Himalaya in this restricted epsilon neodymium, epsilon strontium space by, in fact, taking these rocks and pushing them up here and getting them commingled. That clearly didn't happen. Yeah, just this is simply the difference in parts of 10 to the 4 between bulk Earth, what the bulk Earth would be today, and the measurement. So essentially, because when you melt the mantle preferentially likes the daughter product relative to the it likes the parent relative to the daughter product. Mantle rocks are going to plot up here. Continental rocks are going to plot down here, and very old continental rocks will plot progressively lower. So the sooner you separate it from the mantle, the sooner you're going to be a whole lot deficient in the radiogenic daughter product relative to what as Sue says, if you put the entire planet into a giant mortar and pestle and crushed it up, it would have that composition today there.
So where does Tibet sit?
Tibet is complicated because we, unlike the Himalaya, where we're really getting a pretty good vertical section, we're looking at surface rocks, And in fact, you know, it's complicated, but Tibet can plot here, 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 or here. Depends. Remember, before Triassic rifting, the Himalayan basement and the Lhasa block were sitting adjacent to each other. So what's happened since the Triassic is the Himalaya, you know, India went away for, you know, 200 million years, and boom, it came back, and for the looks of it, just about, you know, found its origin.
It's just too much, guys. You can't fucking do that. It's too convenient over and over. How many conveniences before we're like, maybe we're just making shit up?
Docking location pretty accurately.
And there is no Xenolith to look deeper a little bit somewhere.
There is in not in the Lhasa block. Further north there are, and they have all the problems that xenoliths have, which is, you know, that you don't, you know, the felsic compositions are unlikely to be preserved because you put a felsic rock in a 1200 degree basalt, it's less likely to survive than a, you know, mafic granulite. Okay.
Okay, I made it halfway-ish. That seems like a good spot to just hit pause. Maybe let me see what he says here.
The Himalayan antithesis is due to decompression melting.
Okay, this is maybe a new theory, looks like. I think he's just going through theories and their issues, so I'm just trying to get a grasp on anything that might be of interest. Certainly the separation process of it all is really interesting. I do believe that the fort, this model here, where there's actually a heat exchange process occurring, like, there's no question that heat exchange happened. So when did it happen? And because it's delayed by so many millions of years according to radiometric dating, they just assume they're not related. But because radiometric dating is not a valid method of determining absolute ages, they are connected. So I feel pretty good about this one, actually, and I'm really not sure, but interested in seeing more about this. Because it's probably revealing to just the sheer amount of energy necessary. Like, yeah, it was a supernova of a particle that's like not a planet, but not that far from being a planet. Like, it was within a planet as a major node of a planet. I mean, it's pretty substantial. It's not just an atom, which it's like, you know, like we say radioactive decay can harm you. So imagine the strength of a particle within the earth that the crust rests on as a pillar when it explodes from the weight. It's probably a pretty big particle. So it probably would have done all this. It just did all this. Alright, until the second half.